Hello students, so in this lecture we will be discussing about mainly the viscoelastic behavior of materials. Now the viscoelastic behavior is found in materials which respond to an applied stress, uh, and they are sometimes fully recoverable, the deformation, and sometimes this stress cause a permanent deformation. And also there is a factor of time associated with them. So let's put it this way. So there will be an applied stress, and corresponding to that there will be a strain or a deformation. There will be a stress, there will be a strain, and another parameter is the time. Now, this behavior is very common in non-crystalline organic polymers. Non-crystalline organic polymers. Now, the time-dependent property or time-dependent permanent deformation, if that is called the viscous flow. It is the time-dependent permanent deformation. It is actually analogous to the creep phenomenon in crystalline materials. So, in this viscous flow is analogous to creep, which is found in crystalline materials. So, in crystalline materials, the property is known as creep, or the study is known as the creep test, whereas in the case of non-crystalline organic polymers, it is called viscous flow. So now let us try to understand what do these actually mean, or how we can quantify, or we can mathematically parameterize a certain situation. Now, this viscoelastic behavior, this has been explained by two models. One of them is called, actually, the model is a single model. It's called a Spring Dashpoint model. As you can see, Spring D model. And the two elements that based upon which these models are fabricated, model stands. One of them is the Maxwell's element, and the other one is the Voigt-Kelvin element. So we'll discuss one of them. So first, starting with what does this Spring Dash model, or the architecture, or the arrangement, or the configuration of the Spring Dashpoint model. So as we all know that the shear strain and the shear stress are linked by this Hooke's law, and from where we are getting this shear modulus. Now, compared to this, there is also in fluid mechanics, there is a law called Newton's law. It is nothing but the shear strain rate related to the stress. So here, strain rate is an important factor, but there was no time dependency in the case of Hooke's law. So here eta is the viscosity, and this mu is the shear modulus. Now this spring, which is considered to be a perfectly elastic material. we are assuming that the forces applied are within the elastic limit. So spring in that case becomes a perfect elastic material. And the dash point is, which represents the viscous part of the model. This is actually a container with piston which is moving a viscous fluid. Now in the spring dash dot model, these two entities are combined. In the Maxwell's model, the combination is parallel. We have a spring which is connected with the dash point. In the case of the second one, White Kelvin model, they are, so this is in series, not parallel. This is in series. The another one, the spring and the container containing the piston, they are in series. So these two configurations are considered. So we start with the first one, that is the Maxwell's element. So what we can see here is the two entities are connected in series here. This is the spring, this is the dash point, and they are subjected to a common stress. And the total strain, however, is combination of or a summation of the strain in each of the sections. However, the strain rate becomes negative in the case of the dash point. So there is a sign change. Sorry, this will be also positive. So strain is actually the combination of strain occurring, and so is the strain rate. If you consider now the total system as a single element, which is the Maxwell's element, then the stress on a single element can be represented as this following equation. However, here an introduction of a new quantity, a new parameter has been thought of, which is nothing but the ratio of the viscosity by the elastic modulus, and that is called the relaxation time. Okay, so this is how you can connect these two entities in a single equation. Okay. So in the Maxwell's model, there are two types of experiments which can be done. One is the creep experiment, another one is the stress relaxation experiment. In the creep experiment, the stress applied is instantaneous and the dash point is response to the viscous strain. So as soon as the strain is removed, there is a decrease. The spring now comes into the picture, and spring then responds immediately to the elastic recovery. So graphically you can see that this is what this creep experiment, this is how we can represent it graphically. The stress has been applied instantaneously, so there is no progressive stress, instantaneous stress, and which has caused a certain amount of strain. Then due to the viscous flow, the strain has increased, and after this point, when the strain is released, the dash point is no longer in the picture. The whole the entity that is solely responsible for the immediate elastic recovery is the spring. So this is how it goes. Whereas in the case of stress relaxation time, which is where the stress is again instant, and then the stress is allowed to decrease as a function of time. So here, as the stress decreases, there is actually an elastic strain to plastic strain that is taking place, a transfer of elastic strain to plastic strain here in this way. So the Maxwell's element thus exhibits elastic deformation and elastic recovery as a solid and viscous flow or creep as a function of time. Next one is where you are arranging the two entities, the spring and the dash point parallelly. Here, in contrary to the previous one, the strain is same in the two entities. The strain that has been applied due to this amount of stress is same, and the stress is actually a addition of the stress being applied to the strain part and the dash point part. Now, if you write the combined Hooke's law and Newton's law, so this is your Hooke's law and this is your Newton's law. This is how they can be represented. So here, what is happening is that the stress is again instantaneous. However, the dash point, that means this one, it provides an initial high resistance. So you can see that the initial high resistance is being provided. So that's how this curvature in plot comes. And after some time, the strain rate decreases. So in this region, the strain rate is decreasing progressively, where when the stress has been removed, the strain then decreases exponentially. Now, in this point, the whole system is as if the spring is supporting the system. And changes while the stress has been removed, the changes in the strain, they are only as a function of time and they are not instantaneous. So this means that there is also no permanent deformation that takes place in the material.